Hi everyone, today we're going to do some cycle analysis. It's going to be fun, so let's get started. It says air undergoes a thermodynamic cycle consisting of the following processes: process 1 to 2 to 3 and 3 to 1. And our task is to figure out what the pressure and volume is for each state by filling out the table here for part A, and part B is to draw a PV diagram. Part C is to calculate heat transfer for process 1 to 2, and the last part is to find the network for the entire cycle. So let's get started. First, we always want to list our assumptions. In this problem, the working fluid is air, so we can assume it's ideal gas. And since it's ideal gas, we can assume that CV is constant. Also, we're going to assume that the mass stays the same during the entire time. Also, we're going to assume the change in kinetic energy and the change in potential energy are negligible. So now we're good with the setup. Next step, we're going to translate English into thermodynamics language in order to make our life easier. So for process 1 to 2, it says constant pressure. So that tells us P1 is equal to P2. Process 2 to 3, it's compression with PV equals to constant. So compression, that tells us V3 is smaller than V2 because we compress the air. They also said that PV is constant. So if you remember from ideal gas law equation, PV is equal to mRT. They said PV is constant. So PV is constant, M mass is constant, R is just a constant, so that's constant. In order to make sure this equation hold true, so we need to make sure that T is also constant. So that tells us that T2 is equal to T3, right? And for process 3 to 1, it's constant volume, so V1 is equal to V3. So we're done with interpreting the problem now. So without even doing any calculation, we can already start filling out the table here. So we already know that P1, now before I do that, I want to put units on all these. So I'm going to stay with all the basic units, so Pascal and meter cubed for pressure and volume. So P1, it's 140,000 Pascal. And V1 is 0.028 meter cubed. For state 2, we know that T2 equals to T3, but that doesn't help. But we also know P1 is equal to P2. So P2 is the same as P1. It's 140,000. We don't know V2 at all. But we do know something about state 3. V1 is equal to V3, yay! So we can put V3 here. The volume at state 3 is equal to the volume at state 1, right? So without doing any calculation, we already fill out more than half of this table. So now we just need to find two values. So for part A, I'm going to change the color a little bit. Or should I stay with blue? Okay, let's stay with blue. So for part A, so I'm going to start here. We need to find two values, V2 first, V2 and P3. So in order to calculate V2, if we look at process 1 to 2, we're given that the work from 1 to 2 is 10.5 kilojoule, right? And work from 1 to 2 can also be written as integral pressure times the change in volume from 1 to 2, right? And we can rearrange this equation because P is a constant, it's constant pressure, so we're going to take out of that integral, and also the derivative of volume from 1 to 2, and then we take that integral, that's just the change of volume from 2 to 1. So that's just V2 minus V1, right? So we know work. we know pressure, we also know V1, we need to find V2. So we know everything, we just need to rearrange this equation and find our V2. So V2 is just work from 1 to 2 divided by pressure, so this is P2, so P2, or it can also be P1 because they're the same, and then plus the volume at 1. Now we just need to plug in on the numbers. So 10.5, since this is a kilojoule, so we're going to 10 times 10 to the third to make it the basic units. And pressure at 2 is just 140,000 plus V1 is 0.028, and that gives us 0.103 meter cubed for V2. Okay, so I'm going to box this answer and put this right here in our table. So it's 0.103. Okay, we're done with V2. Now we're going to calculate for P3. Right, I'm going to change to a different color. So also I'm going to do this so we don't confuse ourselves. So for P3, if we look at process 2 to 3, it says PV is constant. So that means P3V3 is equal to P2V2, right? Because they're always the constant values, right? So then P3 is just P2V2 over V3. And we know all the numbers, so we're just going to plug and chug. So it's P2 is 140,000 times V2 is 0.103 divided by 0.028. And that gives us 575,000 Pascal. Okay, I'm going to box this answer and put that value in our table as well. Sweet. So now we can proceed to part B, which is the PV diagram. So I'm going to change to a different color again. We're going to use green. Okay, so PV diagram. We're going to have P for the y-axis and V for the x-axis. Okay, so from state 1 to 2, it's constant pressure. So if we start here as state 1, it's going to be a horizontal line because P is constant. So it's just like, it's just a horizontal line here. So this is going to be state 2. And from 2 to 3, PV is constant. So we also said T is constant, so it's isotherm. So isotherm is something like this. So it's a little curvy because it also tells us PV are inversely proportional if you look at our ideal gas law equation. So here P is just mRT over V, right? So it should be an inversely proportional line here, like this. Make sure it's a little curvy, okay? And from 3 to 1, it's isochoric because the volume stays the same, so it would just go straight down back here. So this is 1, 2, and this is 3. Okay? And we're going to talk about part C and D in the next video. I hope you think this is helpful. Thanks.